Hello, I am Jim Corkins, and this is uh, the continuation of rotational motion, and we have now reached torque and moments. So what we're going to go through is we're going to go through uh, what is torque and moments, same thing, uh, in 5.3.0, and then we're going to study statics in 5.3.1, and then dynamics in 5.3.2. And all of those basically encompass torques and moments that are either at they're torques that are at standing still, or with dynamics. That was statics. With dynamics, it's where they're rotating at some acceleration. Okay, so please do your reading. If Here's the list of reading. If you're in Physics 101 and Physics 111, please read OpenStax in these chapters and Survey this chapter. If you're in Physics 121, please read these chapters and Night chapter 12. And if you're in any of these courses, any of the CLEDA book, please read chapters 9 and 10. Okay, let's get started. So what is torque? Well, torque is it's basically Newton's second law, but applied to rotation. So torque is a rotational force, and that will eventually cause some type of acceleration. So let me go ahead and mark this up. So I'm going to hit the comments and hit my little pen button, and then here we go. So we were talking about Newton's second law. We have this as the linear interpretation. Now we're going to have torque, which is tau, and that's going to be R cross F. Actually, I should say this. It's actually moment of inertia times alpha. Okay. We'll learn later on that that this is actually the sum of all your torques, and that the best interpretation of torque is going to be the length of the moment arm times the force, cross product of the force. Okay. So these would be the sum of all the forces. This would be like mass times gravity times how far it is away from where the pivot point is. So we're going to talk a lot about all these torques, but really basically the basic understanding of torque is it's a force about a circle. Okay. There's some things that you need to know. Torque is dependent upon the magnitude of the force, F, the direction in which it acts. So counterclockwise is going to be positive z according to the right-hand rule, and clockwise will be negative z according to the right-hand rule. Okay, so that's the direction at which it acts, and the point at which it is applied to the object. So what they're talking about here is if you have an object just like this, just a stick, and let's say it's rotating about this point right here. So this whole thing is just spinning. This whole thing is now the lever arm. Okay. Well, if you apply the force here, and let's say it was a downward force, F. Well, the magnitude of that force is important. So the larger this is, the more torque, since torque is R cross F. So the higher the torque, the higher the force, the higher the torque. So increasing that will increase the torque. The direction in which it acts, in this case, this force would be pulling down on this lever arm and cause it to start spinning clockwise. So this would be a negative torque. And then finally, the point at which is applied to the object right here is the distance of the force to the pivot point. So this distance from right here to right here is the distance r. Okay. We will find out later on that this force has to be has to be perpendicular to the lever arm, and that's why this is an X. That's the cross product, meaning only the perpendicular part of the force contributes to torque. Okay? So let's get into this. Okay? As we just introduced, torque is equal to the lever arm cross the force. So torque, which is this tau, that's equal to R cross F. Okay? Okay, so that's the basics of it. But what we're going to find out is that cross product is when you utilize this cross product means R has to be perpendicular to F. That the perpendicular portion tends to be sine of theta. So, for example, we'll get into this more in the next slide. If you have that same object spinning, and let's have it start spinning counterclockwise. But let's say it's being pulled up at an angle of, I don't know, 30 degrees. So this part of the force here's the force F. And let's say it's being pulled by some force up and to the right. Well, what we're going to find out is that if we break this up into its X and Y components, this force, okay, right here, that this part of the force right here is F cosine of 30 degrees. This part of the force right here is F sine of 30 degrees. So what you're going to find out that if you applied a force right here, the F cosine of 30 degrees is just going to be pulling this entire object just to the right. That's what this F cosine of theta is doing. This part of the force, F sine of 30 degrees, is going to make it spin counterclockwise. That's the only part of the force that's going to make it spin counterclockwise. This F cosine of 30 degrees is only pulling the object linearly, so just to the right. It won't contribute to spinning it up or down at all. So that means the F sine of 30 degrees portion, this vertical portion, which ends up becoming perpendicular to the lever arm, only that part of it that is perpendicular to the lever arm is going to contribute to the torque. So this cross product means that these two things have to be perpendicular to each other. Okay? And if you think about it a little bit, let's think about these as proportions here. All right? Let's think about proportions. So if you stacked, so let's say this is your arm, and this is like your elbow right here, and you've got your arm stretched. This is your shoulder joint, and then here's your elbow right here, and this is where your hand is, right? It's actually not bad. Surprised myself. And we're looking down on your shoulder joint, right? So if you applied a force, let's say you're holding a barbell or a dumbbell right here, right? Actually, let's say we're looking at it from the side. Let's say you're holding a dumbbell right here. So this is you're holding your arm out to the right, and we're just standing right behind you looking at you holding a dumbbell, okay? All right? Well, here's why the distance to the lever arm matters, right? So at this distance, if you're holding the weight right here, and at this angle, the weight would just be pointed straight down, right? So that would make it perpendicular to it, right? So this part of the torque right here of this dumbbell is perpendicular to the lever arm, and it's a full distance out. So since this distance is really high, the torque is going to be high. You're going to feel it's going to be harder to hold this dumbbell out right here at this point, right? But if you've ever been to the gym, you've always seen some big guys, and they tend to bend their arms. And they're holding the weight right here, right? And they'll bend their arms quite a bit. And this weight's going at mg right here. And let me do this. Let me try to stack it up even with this other picture so we have a good distance to it. So, and I'm actually going to make it a lot crazier. The shoulder joints at the same place. And let's just say you're bending your arm an extreme amount right here. That's supposed to be your thumb. Let's say here you're holding the dumbbell like this. This dumbbell is going to be pointing straight down the same amount, so that's mg. But if you look at it, that force is really just attached at the elbow, right? So that force is actually attached right here at the elbow joint, right? Right here. And so analogy-wise, that's like you having the same force, mg, attached right here at your elbow. Yes, I know you bent your arm and that kind of stuff, but it's still, that force really is just at your elbow joint. And so that distance to your elbow is about half the length of your entire arm, right? So that would mean the torque due to that guy is going to be R over 2 times F. So this is, at the full distance, it's 1 RF, right? For this full one to this first case, it's that. But here, it's just going to be half that force, right? So if you're bending your arm, you're actually, during, the lateral raise with your shoulders with the weight, you're actually, you're essentially lowering the torque on your shoulder, right? And I don't know if that's better for protecting your shoulders and all that kind of stuff. I'm not sure about that, but what I do know is it is lowering the torque, right? An interesting caveat to this, so even though that seems like it's a bad thing, well, if you have a wrench here and you're trying, if you have a wrench and here's the nut right here, so let's draw, half attempt to draw a wrench. Yeah, that's pretty terrible. Anyways, it looks like a bone. Anyway, so here's your wrench and here's a nut right there, and let's say it's a stubborn nut, and so you're trying to loosen it, right? So you're applying a force. You'll also notice if you apply a force perpendicular to the lever arm, unlike this case up here, perpendicular lever arm, you're probably going to have a better time breaking the rust and causing it to unstick, right? So that force is there, right? But you'll notice that if you're pulling it, and this is only distance R, right? One trick that we've often used, and this is hopefully you don't break the nut itself, but is to actually take a pipe or something and fit it over the end of the wrench so that you can increase that force distance. So by putting this pipe over the edge of this, well, now you've actually doubled the moment, right? Doubled the distance. So that's now 2R cross F, which is twice the amount of torque that you'd be applying to this. So those are basically the important points of what torque is, okay? So let's try learning what torque is by applying it to 3 situations, okay? So let's say you had 3 situations where you apply the torque, and we're going to assume the distance here to this force is the same as this distance, and we'll call that a distance R. So this is distance R where the force is applied to this. I'm actually going to just write that right here. This is a distance R of this force where it's applied to it. And this is a distance here. This force is a distance 2r. Okay. Not only that, let's say this force is at 30 degrees, at a 30-degree angle. And let's say this force right here, it's indicated that that's 90 degrees. And over here, it's also going to be 90 degrees. Okay? So just take a moment, and I want you to try not to read this above, but like rank these from largest torque to smallest torque in terms of R, F, and in terms of R and F. That means you're probably going to have to do some trigonometry on 30 degrees. Okay, so pause video and try to rank each one of these as producing the most amount of torque to the least amount of torque. Pause the video now. Okay, we're back. So let's do each one of these in order. Let's just figure out the torques of each one of these. So here we go. This torque right here is going to be the distance R. And this is going to be, this force right here is at 30 degrees. So the force F is at 30 degrees. And we know only the perpendicular portion of that force is to contribute to the torque. That F sine of 30 degrees is actually going to contribute to the torque. So this distance to here is going to be R. And this is going to be F sine of 30 degrees. Well, the sine of 30 degrees is actually 1/2. So this is going to be RF. This is going to be RF over 2, right? So this is going to be F times 1/2, which is just F over 2. So RF over 2. Okay? Well, let's try this one. This torque is going to be the same distance R, and it's the same force F. All these have the same magnitude force F. But this is at the angle of 90 degrees. Well, sine of 90 degrees is just 1. So this is just going to be R times F, right? Or just 1 RF if you wanted to think of it this way. All right. This next one right here is going to be equal to R. Is actually going to be 2R. I should be careful. I wrote 2R where the force is attached. And that's going to be also F sine of 90 degrees, which is actually just going to be 1. So this is going to be 2RF. Okay, well, what we've made is an analogy that this object here is going to be, this torque for this first one is going to be 1/2 RF. This next one is going to be 1 RF. And this last one is going to be 2 times RF. Okay, so ranking these from largest torque to smallest torque, this would be first, 2 RF. This would be next, 1 RF. And this one would be least. It would be 1/2 RF. So it's interesting that even though you have the same force applied to each one of these, it depends on the angle, okay? And it also depends on the distance as well. Okay. By the way, all of these would be creating a positive torque because all of these forces would spin it counterclockwise, which is positive z. All right. So this is Knight's. This is from Knight's textbook, and this is a great way to look at torques and pivot points. And Knight does a really good job of breaking down force, in this case, force and torque and pivot points, right? So what they're pointing out here is that the direction of the force F is pointing basically straight up, okay? And that the moment arm extends, an alternate version is a moment arm extends from the pivot point to here. So there's an alternate interpretation, I guess, when I'm kind of linking to this, that you don't have to necessarily take this force sine of 30 degrees, a perpendicular part of the force. You could actually, if the object is bent like this, what you could say is that this part of the pivot point right here is going to be F sine of phi, okay? So there's two ways to do this problem. You could kind of curve your head and keep this as the distance r, and this is the force F sine of theta, okay? And which would just produce this distance here. Here's the pivot point, distance here, the force is attached to this. Even though this is right here, it really is this force is actually attached right here. Okay, that's really F sine of phi. Okay, so this is going to produce a force F R F sine of phi. Well, there's another way of doing this. Okay, oftentimes if it's turned like this, it's kind of hard to picture things, and a lot of times what they'll do is they'll give you the angle here, theta, phi, or they'll give you the angle here, theta, and they'll give you the force as going up at some angle like that, right? Well, if you now imagine, instead of dealing with a force right here, is if you draw a line through the center, in line with that force, right? And we're going to make a 90-degree angle right here, and we're going to call this another distance here. Well, now we've turned our r into a hypotenuse, and this part of the force, okay, this part, the force now is parallel to this line, but this distance right here is perpendicular to that line. So, and since we know torque has to have the r has to be perpendicular to F, meaning that these guys have to be perpendicular, you don't necessarily have to take the perpendicular part of the force and then use this as r. What you could do is take the distance r as the perpendicular and then multiply that interpretation of the perpendicular r times F. So let me show you right here. If this is the hypotenuse, this is going to be r. R parallel is going to be r. It's going to be the hypotenuse cosine of phi, right? Well, that is in line with the force. It is not, it's parallel to the force. We need the perpendicular part of the force. Well, the perpendicular part of the force is going to be r sine of phi. So that is going to be that part of the force. So now when we compute the torque, we could say r sine of phi times F, and then rearrange it to the proper form, which is RF sine of phi. I guess what I'm saying is there's two ways of doing these problems. If everything is aligned this way, where the lever arm is horizontal, this is probably the best method. The first method I showed you, where you use force and do the perpendicular part of the force, that's probably the easiest to do, okay? But some problems, they will show the lever arm is kind of pivoted a little bit. It's been turned a little bit. And in this case, it may be easier to, instead of doing the perpendicular part of the force and reinterpreting all these angles, because your geometry has to be pretty good to do that, you could just look at the moment arm itself, the distance of the moment arm, as the perpendicular part, which we just did here, okay? So I kind of like to do them both just to double check my work. So in later problems, when we're actually doing that, I'll show you how to do both methods, I guess. That's what I'm saying. Okay? All right. Anyways, this is basically the interpretation of those different forces, right? So again, this is talking about the perpendicular part. The one that's going to create the most amount of torque are the ones that are perpendicular to the lever arm. This part and also this part, this force, and this force is going to be maximum torque. Maximum torque. This part of the torque is going to twist it twist it counterclockwise. So it would be a maximum, clockwise, I should say. This is going to spin it clockwise. So clockwise, which is going to be a negative torque. So this is negative torque. This part will start to spin it counterclockwise, which is going to be a positive torque. Okay. And then this part of these radial torques, which are parallel to the lever arm. If the force is parallel to the lever arm, which is a kind of a radial, it will either shove the wrench here into the nut, or in this case, pull the wrench out of off the nut. Okay, and we've talked about this one. This is going to produce, and if this is 30 degrees, this will produce half the max torque. So this is be torque over 2, and it'll be positive since it would be spinning it counterclockwise. This torque right here is going to also be half that, but it will be negative torque. And it will spin it clockwise. Okay? All right? So that's the basics of torque. Okay? So let's practice a couple of these. I just put this one here just to let you know that eventually what we're going to be doing is we're going to be summing up we're going to be given problems in the next part with dynamics, where you're going to have a bunch of different torques. You got torque 1, and this torque is spinning it clockwise. This torque right here, this torque would spin it counterclockwise. The second torque would be spinning it clockwise. So you've got all these objects, all these forces attached to a lever arm, spinning it clockwise or counterclockwise. So T1 and T3 are spinning it something counterclockwise, while T2 is spinning it clockwise. Well, you're going to eventually sum those torques and set it equal to I alpha. Okay. Basically, just like with summing forces, which you are going to do here as well, you'll sum the forces in the x direction. You have force 1 plus force 2 minus force 3, and we would set those forces equal to mass times acceleration. In this case, acceleration in the x direction. You're going to do the same thing with torques. So we'll talk about that in the next part. The next part, though, since it's not going to be moving, alpha will end up being 0, so you don't have to worry about moment of inertia just yet. We'll worry about moment of inertia as applied to these cases in dynamics, energy, and rotational momentum. Okay? All right. Let's do a little problem. Suppose you've got a 2 Newton force that is applied at different parts of the same lever arm. Okay? So A, it's this lever arm is distance, the force is a distance 1 meter away. B, it looks like the force is at a half distance from the pivot point. The dot is a pivot point. C, it's a full distance, 1 meter. D, it's also at a half distance. E, it's at a full distance, right? And D and E are 4 newtons, and E is at a 45-degree angle. So what I want you to do, again, is I want you to rank all these torques from largest to smallest, okay? So rank all these torques from largest to smallest, and let's see what you get. So please pause the video now. All right, let's try it. Let's sum the torque at A. So first of all, let's get directions from this. So A is that 2 Newton force is gonna cause it to spin. It looks like counterclockwise, okay? So A is gonna be the torque at A, and that is a full distance away. So that's gonna be R times F times sine of 90 degrees, sine of theta. This is a basic format, right? But our torque is going to be 1 meter away, and it's going to be times 2 newtons, and it's going to be sine of 90 degrees, which is just 1. I don't know if I want to write that anymore. It kind of makes it look a little bit busy, the equation. But this is 2 newtons, so this is going to end up being 2 Newton meters, okay? And that'll be a positive torque, okay, since it's moving counterclockwise. All right, cool. That torque A is done. Let's try torque B. Torque B is a distance a half meter away, but it is also a 2 Newton force, and it's also at a 90-degree angle as well, okay? So torque B is going to be half of the 2, so it's 1/2 times 2 newtons. This is again equal to 1. So this is going to be 1 Newton meter. Torque C is straight out. So it's at 180 degrees. And it's at distance 1 meter. I should have put a half meter here. This is 1 meter. Okay. So that's torque C. So torque C, if we're just going to go by the math, we know that it's not going to apply a torque, and this should work out to be 0. But let's just make sure. So that's 1 meter away, and it's 2 newtons times the sine of 180 degrees. Well, sine of 180 degrees is just 0. So torque C is going to be equal to 0. All right. Torque D is at 90 degrees, and that is at a half meter out from the pivot point. So torque D, I should say, is going to be a half meter out. It's 4 newtons, and it's at 90 degrees, which is equal to 1. So torque D is going to be equal to, what's 4 newtons divided by 2, so that's 2 Newton meters. All right, finally, this force of 4 newtons is attached 1 meter out. This part of the force here is going to be 4 newtons sine of 45 degrees. So that's the part of the force that is at a perpendicular to the lever arm. So torque E is going to be equal to 1 meter times 4 newtons times sine of 45 degrees. Well, that's too much math for me, so I'm going to use a calculator on this one. Pop up the old calculator. So that's going to be 1 times 4 times 45. Actually, it was 1 times 4 times, and now I'm going to do 45, and sine of that, in parentheses, equals, so 2.82, so 2.83. So this is going to be 2.83 Newton meters. So it looks like it's kind of interesting when you look at these numbers here and then aligning them from largest to smallest. It looks like torque E is the greatest, and then it looks like torque D is going to be equal to torque A, and then torque B is next, and then finally is torque C. And all of these will be positive torques. So all of these will be positive torques, spinning it counterclockwise, except for, obviously the zero torque one. But it's interesting, if I was just going to scan this, I would think this would have the greatest amount of torque, right? Because it's at 90 degrees and it's double the other three forces. But the problem is it's at a half mark. So I would have actually not guessed this would have been as great as it was. I would not have guessed that as the winner. So it's interesting. By the way, this is equal to 0.707. You should probably know sine of 45 degrees is 0.707. But I just wanted to do on the calculator to just double check. Anyways, it's just kind of surprising by guessing certain things, and that it's always good to double check, okay, and use proper form when you're doing it. All right, let's move on to some a really good problem, okay? So here we have a problem. We have Luis has a 20 centimeter long or 0.2 meter long wrench, and the force of 100 newtons is going to be attached there. So this is a 0.2 meter long wrench, and the handle is tilted at 30 degrees above the horizontal, and it looks like Luis is pulling it at 100 newtons. And the question is, how much torque does Luis exert on the nut? So let's do this problem, and I want to do it both methods I kind of showed you. But I'm going to grab it, screen grab it. We're going to put it into our whiteboard. Okay. And let me do something else too. I'm going to take this, I'm going to take another part of it. I'm just going to it's not enough. I'm going to grab, actually I'll do it this way. All right, let's go ahead and drop it in there. So I just wanted to have the problem here so that we're going to do one way and then the other way. Okay. So the first method we're going to do is where we're actually trying to figure out the angle of the force, the perpendicular part of the force, and then multiply it by 0.2 meters and then figure out the torque that way. Okay. The second part is over here. What we're going to do is find we're going to try to take the perpendicular part of the moment arm distance and then multiply it by 100 Newton force and then figure it out that way. So let's try both ways. So we know this force is attached 0.2 meters away from the pivot point, which is this nut right here. And since it's tilted at 30 degrees, we're probably going to have to do some triangles. Okay, so let's do this. Let's figure out this distance here. right there. Oh, well, not that distance, but I'm just creating triangles. And, oops. And this angle right here. Okay. All right, here we go. So we know this is 90 degrees right here. This is 90 degrees, this is 30 degrees. So we know this is 60 degrees. Oops, 60 degrees right there. Well, if we take this part right here, and I'm going to draw another line through this. Looks like arrows are the way to go on here. Well, this part, that's 60 degrees, okay? Well, what we've done is just we drew a line through here, and this is 90-degree angle. This is a 90-degree angle right there. Well, actually, think about it. This whole thing right to here is 90 degrees, okay? Well, if that's 60 degrees, and this angle to here is 90 degrees, and this is 30 degrees, right? Well, here's where we need to break from the formula that tau is equal to r cross f, which is equal to rf sine of theta, okay? Well, in this case, the perpendicular part of the arm is actually this part right here, which makes a cosine it's the cosine portion of this 30 degrees. So this being always sine of 30 degrees is not too true. We need to actually concentrate on what part of the force is perpendicular to the lever arm. And in this case, since this is 60 degrees, and you could argue that that is f sine of 60 degrees. Right, and it still holds true to this, but rather than that, since I've indicated this as the angle 30 degrees, this is going to be f cosine of 30 degrees. So the torque here, which is going to be equal to r, which is 0.2 meters, cross f. Okay, well that r is 0.2 meters, and that F is 100 newtons, but the perpendicular portion is the cosine of 30 degrees, right? It's this part here. This is perpendicular to the lever arm, okay? So working this out, what we're going to get is I'm going to start with 30 degrees cosine, multiply that by 0.2, multiply that by 100 newtons, 17.32. So this is going to be 17.32 Newton meters. Okay. That was interesting. Let's try the alternate way. What I'm going to do is take this, and I'm going to make a triangle here. Okay. Just like it was shown. in Knight's example. Come on. There we go, here. All right, so we made a triangle, okay? So this part of the triangle right here, again, which is the hypotenuse, we're going to concentrate on distances, and let's not worry about this red arrow right now. So this part of the triangle is 0.2 meters, okay? And that this is an angle of 30 degrees, right? So this distance is 0.2 meters. This is an angle of 30 degrees. Well, which part of this, so this part right here, this black line is parallel to the red line. So this is R equals, by the way. So that's R parallel. Well, this is the perpendicular portion to the lever arm, right? This is making a 90-degree angle to that line right there. That is going to be R, and that is going to be cosine of 30 degrees. Okay? So tau, which is equal to R cross F, which is equal to R perpendicular times F, well, that's going to be equal to R cosine of 30 degrees times F. So in other words, this one here is going to be equal to RF cosine of 30 degrees, which again is 0.2 meters times 100 meters times cosine of 30 degrees. So our tau is going to work out to be 7.32 Newton meters. Okay. So here's both methods on how to do this problem, where you concentrate on looking for the perpendicular part of the force, and so you have to do some trigonometry and some concentric triangles right here, just like we did, and you just leave R as the given value of 0.2. The other method is where you're actually going to be twisting R but leaving F alone. Here, you're looking for the perpendicular part of R that's perpendicular to F, right? So I did a little triangle, and in this method, you're probably going to have to assume that R given is going to be the hypotenuse, okay? So both methods are valid, and both methods result in the same way, right? In the same thing, okay? And these would both result in a negative torque. I should have indicated that. I'm very sorry. So this force is going to spin this wrench clockwise, and this one is going to do the same. So this is going to result in a negative torque. Okay. And so that's the method that that second method is what Knight is using. He's basically saying, okay, well, I'm going to keep the lever arm distant. I'm going to leave the force alone, but I'm going to keep the lever arm. I'm going to twist the lever arm, or find the perpendicular portion of the lever arm distance of 20 centimeters. So actually, it looks like he did both ways here too. Oh, that's interesting. So he found it twisting, finding the torque part, and then he also found twisted the lever arm part as well. So he did it both ways. Well, that marks the end of this part of torque. Next part, we're going to move on to statics as applied to torque and moments. Okay? Thank you very much. Have a nice day.